So, hello everyone. Today we're going to talk about physical implementation of analog integrated circuits. The outline of today's lecture will be: first I'm going to talk about the CMOS process stack, then I'm going to talk about how active components are built, then I'm going to show how passive components are built, then I'm going to talk about a little bit about the interconnection parasitics and their impact in analog circuits. And then we go to analog layout techniques. Finally, we will run a big example in which we show how to lay out an op-amp. That includes both active and passive devices. So here we can see the stack of a typical CMOS process, CMOS bulk process. So we have that we have the transistors. We see the transistors are built over a P substrate, and then we have two types of transistors. We have the NMOS transistors that we can see here. We have N plus diffusions, we have the gates, we have contacts that bring the source, drains and gates up to metal 1, and we also have contacts to the substrate. So we have contacts to the substrate that guarantee that the bulk potential is close to the transistor is constant. We have also, so this is an NMOS transistor, NMOS. And then we have also PMOS transistors. The PMOS transistors are built over N wells. So there is an N well over the P substrate, and then we have P plus diffusions. Same thing, we have contacts that bring the source and drains up to metal 1, the gate also to metal 1. And inside the N well, we have an N plus contact that bias the substrate. So it is very important to remember that every time that we have a P to N junction, what we have it is a diode. We are building a diode between the P. This is the P substrate here. This is N, so we are building a diode. Here we are also building a diode. Okay, so there is a diode going in this direction from the P well to the N diffusion. So we have diodes here and diodes here. So under no circumstance these diodes should be forward biased, because it will immediately cause a large amount of current flowing and the device will get damaged immediately. So that tells us that the voltage connected to the N well should always be higher than the potential to the substrate. Above M1, we might have different metal layers for doing interconnections, and that depends on the technology and the options of the technology. So easily we can have 4 or 5 metal layers, and when we are going up they start to becoming thick, because the idea is that they will start also bringing power lines. So there will be VDD and ground with a large amount of current. So there is a more for power interconnections. At the top typically you have thick metals also for distribution of power with thick bias. We will talk a little bit about special modules like this one for building capacitors. So we will talk about a bit later. So a bit more complicated process and more advanced process is a triple well process. So in a triple well process we have the opportunity of having both N well and deep N well sitting over the substrate, and that will allow us to have isolation of the transistors. Okay, so now we will have a diode here, there it is here, P So we have a junction here, but our NMOS transistor that is sitting here, or NMOS transistor, it is not connected directly to the substrate. So typically the substrate, and then I go back to the previous, to the doing well process. Typically the substrate has a low resistivity. Okay, so the resistance of the substrate is very low. So noise can travel through the substrate and couple to our devices very easily. So this the resistance of the substrate is not very high, it is actually low. And for instance, if we have digital circuits close to our very critical analog front ends, noise can couple through the substrate. So very noisy signals can just travel through the substrate and reach the bulk of under or transistors and start introducing coupling noise to our circuits. So triple well process introduced this deepen well, and the deepen well isolates our devices. So it isolates our devices, and then we have the possibility to put our NMOS devices to put another P well under the deepen well, and then what we have it is that our NMOS transistor, it is isolated from the P substrate, at least at low frequencies. Remember that at very high frequencies the diodes also have capacitance, and then they start short circuiting at very high frequencies. But at relatively low frequencies we have complete isolations of the NMOS devices, and we can put also N-well devices. Also the N-well devices by definition are isolated also, no? They have an isolation here. So the big impact, the big improvement is actually for the NMOS devices that are not sitting anymore directly over the P substrate, because then there is no isolation here. So these are the triple well process. Normally is an optional module that can be added to the fabrication layers. Okay, so those are the typically the CMOS process that we have available for with the NMOS and PMOS transistors. There might be other processes that include high voltage devices, but we are not going to talk about those ones here. Now let's talk about the active components, how they are built. So the typical devices that we have available in almost every process design kit and almost every technology is NMOS and PMOS transistors. Then, since we have diffusions, N plus and P plus diffusions, we have P substrates, N wells, P wells, there is always the chance to build the junction diodes. So we have also diodes in our PDKs, and diodes are typically used for ESD protection. Okay, so therefore ESD protection are also for antenna also. Antenna protection, so in digital circuits. So this and also for analog circuits in some cases they also need the protection. So they are we have available junction diodes, and then also we have bipolar junction transistors. But these transistors typically we don't use in CMOS processes. We typically don't use for amplification unless the process is by CMOS. So most of the time in CMOS processes, the BJT transistors, the bipolar junction transistors, are just made with parasitic junctions, and they are only supposed to be used as band gap references to build voltage references that are constant over temperature, or as ESD protection, as backsnap transistor. So those are the uses that we have in CMOS processes, but you have to be aware that there are some BCMOS processes in which there are bipolar transistors that are designed to be part of the signal paths. And bipolar transistors have some very interesting properties, large FT, high gain. So they are very interesting for in some high frequency applications. But for the things that we are doing in a pure CMOS process, they are mostly used the parasitic BJT transistors for band gaps and ESDs. As I mentioned before, there might be additional transistors. For instance, high voltage transistor, diffusion MOS transistor. So those are specialized devices used as switches normally, and that can tolerate high voltages like 20, 30, 40 volts. So they are special modules for special industrial applications. There is the BJT transistor for RF and power that I mentioned, typically BCMOS processes. There might be other devices that are also available, like the Schottky diodes. They are diodes with very low forward biasing voltage. And there might be other modules that are available also for optics, for instance, optical modules. But the ones that you will typically have in a CMOS process are at least these ones. So let's take a look to the NMOS and PMOS devices. So we have here the NMOS device, and we see that the NMOS device is built over a PWL, and we have N plus diffusions, and technically speaking they are exactly the same dopings, the N plus regions here, so we can put actually the drain in the left and the source in the right. It really doesn't matter. The drain and the source are defined by the voltage that we apply over the terminals. We have the poly over the very thin dielectric here, and this is a poly that has a polysilicon that typically has a low resistivity, and that is connected to the gate terminal. And there is a bulk connection close by. It has to be close by so that it is biasing the bulk of the transistor. So this is going to place the voltage under the transistor to a particular level. And we have exactly the same thing for the PMOS, but for the PMOS it is sitting over a N-well. How do we lay out the device? So from the top we draw the poly. The poly is a rectangle typically, and then a diffusion, and the tool internally it is going to cut it is going to do the XOR for the transistor, and it is going to just create the source and drain regions. So actually the transistor is only the part that is located here, so it is only this part, the transistor, the active part of the transistor. And then there is a diffusion, and then this diffusion will have to be connected, and there will be contacts on the top. Of course, we will need to put the contacts. We will need to put contacts, and contacts, so that they can go to metal 1. Okay, diodes are made using parasitic junctions. For instance, we have a P substrate, there is a PWL, and then we can put an N plus diffusion. So we put an N plus diffusion, and what we are effectively doing it is we are creating a diode in this direction. Okay, so PN junction. So we have a diode in this direction, and then the PWL is sitting over the substrate, so it's technically speaking a short circuit to the substrate, and the substrate it has to be grounded. And very close by to the cathode we will have that the P plus it is there is a P contact, and then this has to be connected to ground. So this diode only works like this. It is one terminal, the anode is grounded, and then the cathode, we can put any kind of potential. Okay, so this is one alternative, and those diodes are typically used as protections. So how can we use it? Very often we have our transistors here, that they look like this, and sometimes we have an interconnection that it is very long. Okay, we have an interconnection that it is extremely long in one metal layer that it is connected here. And if it is very long, there will be the problem during fabrication that it gets charged. The gate of this transistor gets charged. So the metal is very long, the area is very long, it is working as an antenna, it is accumulating charge, and then it can damage the device if it exceeds the maximum tolerated voltage for the gate. And then to avoid that problem, sometimes we need to put a small diode here, reverse biased, so that the parasitic resistance of the reverse bias diode will discharge this line. Okay, it will discharge, and it will avoid that it gets to the voltage that it damages the device. So it is working as an antenna protection. They may also be used as ESD protections, and then we will talk in next course about how to build how ESD protections are built, but they might also be used for ESD protections. A little bit more useful it is if we put an N-well, like we put it here, an N-well, and then P plus and N plus regions inside the N-well, and then we can have a real diode that we can change the voltage at the anode and the cathode, as we see here. So the diode, it is being formed in this direction, and then the N-well and the N plus, they are technically speaking a short circuit. So there is very low resistivity between the N-well and the N plus region, so it acts like a short circuit. And then there is another diode that it is being formed. It is this one here. From the P substrate to the N-well, we have another PN junction. So now we have the following diode. So we have the following diode here, and then we can put we have more freedom to put the different voltages here around the diode. And that is how we will lay out this device. So we can have also bipolar junction transistors, and then here we have an example. It is not really so different than the junction diode that we see here. So it is changing distances and dopings. It is possible to create this bipolar junction transistor. So we see that the diode will work like this. We have the base terminal here, P to N. We have junction in this direction, and then we have that is a really silly drawing. We have like this. So here we will have, let's say like this. Okay, we will have the P to N. We will have the emitter to the base, and then we will have here from the N to the P, we will have the other terminal of the transistor. And then we can see that this is always grounded because this is connected to the substrate. So in this This bipolar transistor, this is a PNP transistor. It's a PNP transistor. There is one terminal that it is always grounded here. So we use this one for bandgap reference typically. That is one of the very few uses that we can have for this device. So it doesn't have a lot of amplification, but so it cannot really be used as an amplifier. Okay, so those are the typical active devices that we have available in our CMOS process. The active devices can also be, we can have also other devices depending on the modules available for the PDK, but those are additional modules. Now the passive devices, we have resistors, capacitors, and inductors. Inductors will be a topic of the radio course. We don't use it at low frequencies, but when you go above 1 or 2 gigahertz, they are small enough to be implemented on chip. On the other hand, we use a lot of resistors and capacitors, and then we have different kinds of resistors. We have polysilicon resistors, diffusion well resistors, metal resistors, and for the capacitors we can build in different ways also. Metal capacitor. We have also capacitors that are built with transistors using the parasitic capacitances, or intrinsic, actually we call it much better, the intrinsic capacitance of the transistors. And we can also build the fringe capacitors. So let's take a look very quick to these devices. So one way to do to implement a resistor, it is just to use the polysilicon, the same one that we use for the gates, to build the gates in the transistor. So remember that under the poly we typically have an oxide, and there is an isolator there, so it is isolated from the P well. But this oxide, this is very thin. It can be just a couple of nanometers, sometimes even less, in modern technology. So we will have a resistor that the first has a relatively low resistivity, and then it has a capacitive coupling to ground, because the substrate it is grounded. So there will be a capacitance to ground and relatively low resistivity. The resistivity can be changed by doping the poly with salicide, so it can be tweaked, the resistivity, using different processes, and you can increase to medium resistivity, so a few hundred ohms per square, or even kilo ohms per square, so they can high poly resistivity. So it is possible to use, and normally we use these ones in analog design. They are very, very common. Then we have that, precisely as we did before with the transistor. In critical applications, we don't want this capacitive connection to the substrate, because there is noise that might be injected in the substrate by a digital circuit. So it might be very strong digital noise as a frequency of the clock that it is being injected here, and we don't want that it couples to a resistor that might be part of a very sensitive analog amplifier. So very common, we use an N-well under the resistor, so that we have a level of isolation here. So we build here a PN junction, and it become isolated. We isolate the resistor from the substrate, and typically we connect the N-well to a higher potential, so this is very well reverse biased. Now we have something that the model will look like this. So we have a resistor, we have the capacitance, and then a reverse bias diode. So it's a 3-terminal device, actually 4-terminal if you include the ground. It is also possible to build other kind of resistors, for instance using diffusion and wells, so they have a particular resistivity also. And then well, the resistor will look like this. We have N plus contacts and on the borders of the resistor, and then we have an N well. And then there will be some diode that it is formed here, a parasitic diode between the piece of substrate and the N well. So that will be the model that we have for our resistor. Now it is possible to use the resistors, but very often the dispersion of the resistor it is very large, so it is not as well controlled as the resistors that are made with poly. But it is possible to use in some applications, for instance, that does not require precision resistors. Protections, for instance, it could be okay. Part of the ESD protections. Now the capacitors, there is a couple of ways to build capacitors on chip, and one way it is to add a metal layer between two metal layers. So we have for instance this metal layer that is called VM, and then over this VM we add a very thin oxide. So here there is going to be a very thin oxide, the one that is here. Okay, this is a very thin oxide, a few nanometers also, and then precisely above this oxide we put some metal layer that is basically just covering the oxide, and then we form a plate capacitance between this cap metal layer and VM, and then we can put a contact, touch the top metal, and then go down, so we have our terminals here down connecting to our transistor and the rest of our circuits. So that is how it is built, a metal in metal capacitor, and then we can control the area of this capacitance to increase or decrease the size of the capacitance. An important detail of a metal in metal capacitor is that there is a bottom plate capacitance that it is being formed here. Okay, so it is this capacitance CB that we put it here. So we have a top plate and a bottom plate. So the bottom it is here, and the top it is here, and the bottom it is here. So there will be this capacitance here that is being formed, and in order to minimize this capacitance we will prefer to use the top metal layers because they are far away from the substrate. We lay out the capacitor like this. Okay, so we have the bottom metal area here, we have the top metal, and then we put contacts. Just put contacts in order to connect to the both sides of the capacitor. This is a linear capacitor. That is made with metal, so it is a very linear capacitor. It's a plate capacitor. Typical values of capacitance that we can get here, it is around 1 to 2 femtofarad per micrometer square. Okay, so this is what we can typical capacitance of a MIM capacitor. So getting like a 1 picofarad will require around 30 by 30 micrometer to get 1 picofarad. So you get an idea how big they can be. Then it is also possible to use MOS transistor as capacitors, and then we can see here we have a transistor that it is built over an N well, and then we have N plus and N plus diffusion regions here, and then we can bias the gate and then we will be forming a channel under the gate. Okay, we will be building the channel under the gate, and then we will be building a capacitance that it is changing depending on the amount of channel that it is formed under the gate. And because we can change it, then it depends on this channel under that it is formed here under. That capacitance, it is variable, so we can change, and it has very interesting applications. For instance, there is situations in which we need to tune resonators in oscillators. So for instance, in voltage control oscillators, we need to tune the frequency of an oscillator, so we will be using MOS varactors. The capacitance, as you can imagine, is nonlinear. It's working on the principle of inversion of a channel in a transistor, so it will be a nonlinear capacitance, so different than the MIM capacitor that is very linear, it's a plate capacitor. So we will not use this kind of capacitor to build the feedback of the amplifiers, for instance. We will not be doing that as a part of our signal path. But we can use, for instance, for the coupling of the power supply. It has typically much larger capacitance than the MIM capacitor, so when we need a large capacitance, we will be probably using varactors, MOS varactor capacitances. So we can use for the coupling of the power supply where we really don't need linearity, we just need a large capacitor. Then we have another option to make integrated capacitor, and is to use fringe capacitors, and then that is basically making interdigitized metal structures, and then these structures have parasitic capacitances. Okay, so they have parasitic capacitances, and then we use all metal layers that are possible, so there will be capacitance in all the metals that are contributing to the total capacitance. Okay, so it is possible to make these capacitors, and the characteristics of these capacitors are the following. So they are not as good as the MIM capacitors, naturally, because in the MIM capacitors we can have a really thin oxide here, which is producing a very large capacitance. So remember that in a plate capacitor, the total capacitance, it is epsilon relative, epsilon sub 0, and there will be multiplied by the area of the capacitance divided by the thickness of the oxide. So very thin oxide will produce very large capacitance, but here we really don't have that. We are limited by the minimum spacing that we can have between the metal layers, and we are also limited by the bias here. Okay, so there will not be large capacitances here, and then we have also that since we have to use metal 1, there is going to be a proximity with the substrate. So these capacitors are not as good as the MIM capacitance, but on the other hand, they can tolerate very large voltages, so much higher voltages than the MIM capacitor. The MIM capacitor, since it has a very thin oxide, it will not tolerate high voltages because it will immediately break down. On the other hand, the separation between the metals here, it is quite large in comparison. It can be several hundred of nanometers at least. So they will not have a breakdown voltages like the MIM capacitors. So they can tolerate easily 30-40 volts without getting damaged. So they will be used in some applications at high voltage, for instance. Okay, well, so we have seen that we have resistors, we have capacitors that we can integrate. Now, very interesting topic is that when we connect our transistors and passive devices, we will be using this metal interconnection that we discussed before, and then this metal interconnection will introduce parasitics. So we'll introduce three types of parasitics. We'll introduce resistance, inductances, and capacitances. And at very low frequencies, the inductors are not so important. Remember that the inductance have a impedance that it is proportional to the frequency. So at very low frequencies, we can disregard the inductive behavior. So they will become very problematic or relevant at RF frequencies. On the other hand, the RC parasitics will impact the analog behavior, and we have really to take them into consideration. So what we do is that when we do the physical implementation, we connect our transistors and our passive devices. We have to extract the parasitics of the interconnections and do a simulation to check that the amplifier that we are designing or the circuit in general that we're designing still accomplishes the specifications. Something very important is that the metal interconnections have a limited capacity to conduct current. So we have to check the minimum width that we want to make or interconnections, because depending on the current that it will pass, we have to dimension this width. Typically the current densities, let's say current densities for metal interconnections can be around the maximum current, around 1 milliamp per micrometer width. So I will, if I am passing 1 milliamp, I will have to make this width larger than 1 micrometer. So this is actually the maximum rating. It means that it will get damaged if I put 1 micrometer. I have to take margins at least twice. Okay, I will take at least twice the margins for, and there is current densities for AC, for DC. So depending how they are defined in the manual, you will have to decide what is the width of the metal interconnection. The same for the bias. So around 1 milliamp per micrometer, it is the rule of thumb, but you have to check it the manual. It can be more or less depending on the material, on the thickness of the metal, etc. So how to lay out a CMOS transistor? Typically we will have that when we design the CMOS transistor, we give a width and a length for the transistor, and very often we will have situations in which the width it is much larger than the length, and it is not really suitable to lay out a transistor like this. For one thing, this aspect ratio will result in very large series resistance for the gates and also for the drain and source. So we will need to split it, and in this particular example we have split this transistor in 3 components. So we can have the transistor like this, and then we can connect together the drains and the sources and the gates. So if we connect the gates together, we can see immediately that the gate resistance has been reduced substantially. So the resistance from this point to this point, and now we have reduced because the larger distance that we have are here and here. So remember, the poly, it is not a the polysilicon, it has some resistivity. It is not like a metal interconnection. So we will want to reduce this resistivity in order to reduce the noise at the gate. At high frequencies, it will be also that resistance reduce also the bandwidth. we can connect here, and then we connect the drains. We can connect probably the drains here like this, and then we can connect the sources in another metal layer. So we can do like this, and then we have the same thing with a different aspect ratio. So if we do like this, then at the end of the day we will have a layout that will look like this. We might also have this kind of layout like this. In this particular case, what we are doing, it is basically to change the number of fingers. We change the number of fingers, and then we are reusing the source or drains. So basically we are abutting these transistors. So if I abut two transistors and I overlap the sources, then this part, for instance, will be overlapping for two transistors. This overlapping drain here, and then I will be overlapping the source of two transistors here. So I can reuse the same area as the source or drain for two transistors. When I do like this, then what I will be changing is only the number of fingers in the transistor. So the transistors have the same dimensions, but it is more compact and easy to draw and low resistivity. So when we are designing, we are typically we might be changing only the number of fingers, or the width and number of fingers, but later at the end, when we have already the real width and length, we will be needing to change to reasonable values during layout, so we have a compact design. So there are some considerations that are very important when it is the placement for matching. So the problem arises from the fact that the process and temperature variations will introduce mismatches between components. The reason for that is that there are not really two devices that are equal. Always due to process difference in the process, we will have that the devices are slightly different. And there are many reasons for this. One reason is that, for instance, the doping might be changing. The doping concentration might change. Etching might also change. So typically devices that are closer have lower process variations than the devices that are very far away. So there is also a distance, let's say, parameter that is involved in the mismatch of circuits. So in transistors, one thing that might happen is that the threshold is not exactly the same, and then we have critical circuits like differentials pair that relies on that the thresholds are the same. So in practice, we will have this problem, and we will need to mitigate this problem. Besides the distances between devices, the mismatch depends on size. So very small devices have very large mismatches. So the effect of process variation, it is more larger for small devices. For very large devices, very large areas, the process variations tend to spread over large areas, and then they average each other. So we avoid small devices in analog design. So small devices are typically used just for making digital gates. In analog circuits, they are very seldom used. And the other thing is that there are some parts of the circuit that are more important than others. For instance, the differential pairs are important. Current mirrors are also important. We expect that the current that we have and the reference, it will be mirrored at the output, but if the thresholds are different, then the mirror will start introduce mismatches also. Precisely as we have a difference between the transistors, we have also difference between passive devices, capacitors and resistors. So here, for instance, we have a fully differential inverting voltage amplifier, and we will expect that these two resistors are the same as these two resistors, so that the gain can be linearly related to only the resistors, but in fact small resistance variations will be introduced, so that will cause that the common mode signals that appear at the input will not be rejected by this amplifier, but they will be converted to differential signals at the output due to the mismatches. Now the problem is that the variations of chip, the variations of parasitic resistance and capacitors on chip can be quite large. So it is not like when we design analog electronics of chip on a PC, on a printed circuit board, that we can just buy components that have very low dispersion, so very high precision. It is not exactly the same. So some of the circuits that we design on board will not work on chip due to the mismatches. So how to improve the matching of the devices in critical circuits? And we have that basically we will need to we can divide the devices in smaller units. So the idea is that we will attack the distances and we will spread the variations on the process on all the devices, so that all the devices face around the same variations. So we will divide the big device in small units. Typically we will be working on differential pairs on current mirrors, so we will divide these transistors in small units, in small devices, and then we will put them together, interdigitize these ones using a common mode centroid configuration. So what is the idea of the common centroid configuration? The idea is that there will be process variations, for instance, going in like this, like the doping of the transistor might change in this direction, this is Y. They might change also in X. There might be also temperature gradients that are, we might have a very hot circuit here on the top, and then there might be temperature gradients. So the temperature here, and here it is different. So to avoid that these variations of process or temperature affect my differential pair, for instance, if it is a differential pair, I can divide the transistor in four, the transistors in the differential pair in 4 components. For transistor A, we call it this one, transistor A, and this transistor B. I can divide transistor B in 2 components, A into 2 components, and transistor B in 2 components, and then I put one of the units on the components here, and the other here, and the other B here, and the other here. And now see how this works. We call this one the common centroid because now we have a very well defined center here precisely in the middle, and then the spread of the process that goes in this direction, for instance the doping of the transistor decreases in this direction, it will affect both transistor A and transistor B at the same time in the same extent. The same if there is a process variation in the Y direction. Both transistor A and B will be affected almost in the same extent. The same can be said regarding the temperature gradients. So both transistors will face exactly the same gradient of temperatures, and that will allow us to minimize the mismatch between these two transistors, because both of them are facing around the same process and temperature variations. On the top of that, we can add dummy structures on the sides, okay? Because we add these dummy structures on the sides, we will guarantee that during fabrication all the sides of the transistor are going to face exactly the same the same process variations. And this is important, for instance, during etching of the transistors. All sides of the transistor will be etched at the same extent. So if we add these dummy structures around, the dummy structures will not do amplification, will do absolutely nothing. Probably they will be just connected to a ground potential, but it will guarantee that these sides of the transistor face exactly the same processing as these sides here, these sides here, these sides here, so that all sides of the transistors will be processed in exactly the same way. So if we have a larger device topology, for instance here, it can be not only transistors, they can be capacitors or resistors. I will be placing dummies around in the border, in the periphery, so that all devices face exactly the same, and I will place it at the same distances, no? So that all devices face exactly the same fabrication processing during processing. There are some cases in which I can simplify the dummy devices placement. For instance, if I have only one row of components, I just need to put one on the border and the other in the other border here, and then that will be enough, because then the fabrication that these two devices are seeing will be exactly the ones that these two devices see. So this one here and this one here will see exactly the same fabrication. If I don't put these dummy devices on the border, these devices will not be seeing the same fabrication as the ones that are in the middle. So it is important to add these dummy devices to guarantee that all these devices here in the middle are correctly matched. The next detail that is very important, it is the placement for matching. Okay, so we have that most devices, as I mentioned before, need to be placed close by, because the distance also contributes to the mismatches. And so we can place them with minimum distances. For instance, the minimum distance between the diffusions, that will be the minimum distance. We can place two devices beside each other in parallel, and then we have the choice: shall we put the sources facing to the left or to the right, or shall we face differently for both transistors? And then for matching point of view, it is much better that the current flows in one direction. Okay, so then both transistors will be equal. So this one, it is not recommended. So if we are placing transistors in parallel with minimum spacing, we should make sure that the sources and drains are facing in the same direction. Now there is the opportunity, as I mentioned before, that we can abute the transistors. So this source, it is if it is the same node as this one, for instance, in differential pairs are a good example. We have the sources of the transistors are the same. We have the option of abuting the sources. So if we can abute the sources, then we reduce the distances. So this will minimize the spatial variations, and give a compact layout. So that might be okay, despite the fact that now the currents are flowing in different directions. So when we have large number of fingers that are abuted, then we will have the same amount of current flowing from the left to right, will be the same amount of current flowing from the right to left, from the drain to source or source to drain, and then those mismatches can be minimized. So at the end of the day, we have to decide whether we are going to use abuted transistors or parallel transistors. Typically, we have to consult the manual to check what is the best from the mismatch point of view. So here I have examples for the common centroid. I have, if I have two transistors, this can be, for instance, a differential pair with transistor divided in two small units. Then the common centroid will be here, and then I can put the devices like this. If I have 4 devices, then I can put the if I divide the transistors in 4 units, then the common centroid will be located here, and I distribute the devices like this. You can see that there is a local common centroid here, a local common centroid here, and yeah, I have distributed these ones so that they are facing exactly the same process variations. We have the devices at the border, 2 devices at the center, and so typically it will look like something like this. Okay, if we have bigger, for instance, if we have divided the multiplier in 16, then our common centroid will be located here, and then basically we reproduce this structure that will appear in this quadrant here. And then we just mirror the same structures. So it is mirrored, making sure that we basically flip horizontally the structure, so making sure that we have 2 in the centers, 2 in the borders, 2 in the middle, 2 in the middle. And then we do the same for the lower part. So clearly everything it is centered around this common centroid. Again, if you see, this is the kind of structure that will appear. For the red. And for the blue, will be like this. For the blue here, it will look like this. So in this way, we guarantee that all the units of the transistors are dispersed around this area, and that they will face around about the same process and temperature variations. So that will minimize the mismatch. It will reduce the mismatch. So the transistors, if we have the NMOS transistor, remember that it is actually a 4-terminal device. We have the bulk, source, drain, and gate, and we have to connect the bulk. How to do that? The NMOS need the substrate connected to ground, and actually we need many substrates connected to ground too. So this has to be very, very good ground, because if it is not, noise will start to couple to the bulk and modulate the threshold, and that will appear at the output of the transistor as noise. So we need to put contacts, and how do we do that? Typically we use rings. We use these kinds of ring structures around our NMOS transistors. They are located very close by. In this case I have a rectangle, but they can take other polygon shapes. They are closed, and they have many contacts to the substrate, so they are isolating our transistor, the transistors that are inside. Here I have 2 transistors that are inside this ring of contact to the substrate. So the NMOS are typically connected to ground, unless there are these triple well transistors that I talked before. Then you have the opportunity to put the substrate contact to something else. We take a look back to the triple well transistor. Then we have in the triple well transistor the contact here, it is isolated. through these PN junctions, so I have the opportunity to connect to something different than ground, the bulk of the transistor. But in a regular NMOS transistor that it is built over the substrate, then I have to connect that one to ground. For the N-wells, we can connect also that N-well to a higher potential. Most of the time you will want to connect it to VDD, but in some situations it may be beneficial to connect to another potential. What is important is to guarantee that this voltage is high enough so that the PN junction that is built between the N-well and the substrate, it is always reverse biased. So here comes a summary for analog layout. First, we have to find which part of the circuit are critical, because those parts of the signal path that are critical, typically differential pairs and current mirrors, they need to be laid out with special techniques. We will need to use common centroid, dummy structures. We have to take consideration of the current direction, and then we have to use the interdigitized structures that we discussed about. This is in the places where we cannot tolerate mismatches. So it is not that all places in the circuit need to be laid out with a lot of care. There are some places like the cascode transistor that they really don't matter so much. The impact of mismatching the cascodes are not so important, but for the current sources, very important. Differential pairs, extremely important to take in consideration the matching. The other thing is that we don't use minimum sized devices. So because then we get hit by all the process variations. So we use larger devices. In analog design, we typically use more larger devices than in digital. We use word rings to connect the substrate, to guarantee a known voltage over the substrate, and to reduce the noise coupling, because that is the way in which we try to isolate the substrate from the external world to contact very nicely to ground. Small distances between substrate contacts, so typically we will generate automatically these rings with a very many contacts as possible. So we can use N-wells to shield devices against the substrate. For instance, resistors and capacitors. They really don't depend on the N-wells for their functioning or to build them, but we can always put N-well under and bias this N-well to VDD or to other potential, and that will basically put a barrier between the device and the substrate. So it will reduce the noise, to decouple to the noise that might be traveling under the substrate. A very important detail, we have to take consideration of the interconnect parasitics. So these resistors and capacitors that are built during the connection of our active and passive devices. They will have an impact in the performance of the circuit. It will never get better. That is also something to consider. We should take a slightly margin when we are designing the schematic, because after parasitic extraction, things normally don't get better. So there will be reduction of bandwidth, there will be coupling. So we have to take some margins. An important detail is that the width of the metal interconnections have to be dimensioned according to the current that is expected to pass. So we have to keep in mind that there is a minimum current density. Typical interconnections, the rule of thumb, around 1 milliamp per micrometer. That is the current density that will cause electron migration, the maximum. So we have to take a large margin from that value. And we shall avoid single bias. Each bias can let it pass as a very small amount of current. So we have to make sure that we use many bias. They also have resistance. Each bias can have a few ohms resistance, so there will have also an impact in the parasitics. To avoid that, we need to put as many bias as possible in the interconnects. Then this is also a tip. There are critical devices, for instance, the input transistors. You might not want to route over these devices because that might influence the matching. So in particular, in differential pairs, maybe some current mirrors that are in the signal path, it's better not to put anything on the top of those transistors, or if it is necessary to put some metal, it's better that it covers all the transistors in the same extent. So for instance, a track might be passing over all the transistors, but not only over a few, because then it will introduce some mismatch. Okay, now we are going to lay out a CMOS op-amp that consists of a differential pair, 2 current mirrors, 2 cascode devices, 1 MIM capacitor and resistor for compensation, and 2 MOS decoupling capacitors. So we will basically see in practice how all these techniques are used in order to lay out this op-amp. So it will look like this at the end of the following tutorial.